Okay, so now we are going to start talking about some more math. Okay, we've been talking about chemical reactions, we've been talking about chemical formulas, so that was our vocabulary. The chemical formulas was our vocabulary, chemical reactions are our sentences, and so now we're going to talk about the math. And so this is more like, in some ways, it's going to lead into more about counting how much stuff we have. Okay, it's going to kind of lead into almost like recipes. So we're going to have to talk about what it means to count atoms without counting them, without actually counting them. So if you had a giant bag of coffee beans, it would take an awful long time to sit there and count out every one of those. It would take a long time. But it is possible to count things in large quantities without actually physically counting them. And that's what we're going to talk about in this chapter. So we'll start talking about that. Same idea. If I had to count all the grains of sand, that would take an awfully long time. Okay, but it is possible to count without actually physically counting them. So atoms and molecules are analogous to our grains of sand. It's really hard to count them. First of all, we can't see them. And second of all, there's a lot. And it would take a really long time to do that. So what we're going to do is we're going to talk about counting by weighing. So let's say I had one of these big bags of M&Ms, and I wanted to count how many M&Ms were in the bag without actually dumping them all out and counting them. And that wouldn't take terribly long, but it would certainly take some time. And so what we're going to do is we're going to use this to come up with the idea of how to count atoms. Okay? So let's say I have my big bag of peanut M&Ms, and I weighed just 10 of them. I took out 10 of them. And I said, all right, 10 of them weighs 8.91 grams. Well, the average weight of just one M&M would be to take that number, divide by 10, right? So what I'm going to do is I'm going to take the whole bag of M&Ms. I'm not going to count them, but I'm going to weigh them. And once I know how much the entire bag weighs, and I know how much one M&M weighs, I can set up like a proportion to figure out how much they actually weigh. So the weight of M&Ms in the bag is 1,587.6. Okay, that's how much all those M&Ms weigh. But I know that just one M&M weighs 0.89 grams. And if I do this as a conversion, now it's been a long time since we've done these kind of conversions. If you notice, grams is on the bottom, so it cancels out. And it's almost like it's a proportion. This many grams is to, stop that. If I wrote it this way, 1587.6 grams is to X M&Ms, as 0.89 grams is to 1 M&M. If I was to cross multiply this proportionally, I would get 1587.6 equals 0.89 X, and I would divide by 0.89, I would divide by 0.89, and I would get X equals. Well, look what I'm doing here. This is a conversion. I put in grams in the bottom because I know one M&M weighs 0.89 grams. When that unit cancels out, that tells me how many M&Ms I have in the bag, and I end up dividing those numbers. Remember, numbers on the bottom divide, just like here I divided, and I'm going to end up with how many M&Ms are in the bag. Actually, I'm going to erase everything. Okay? So, counting by weighing works when items are all about the same size and mass. Now granted, the M&Ms, if you remember when we did the lab with the candy, they're not all the same size. Some of them are chipped, some of them are deformed, but the closer they are to being exactly the same, the more accurate that number becomes. So this is an estimate, because I know that that's an estimate of the average mass, because sometimes M&Ms don't weigh the same. Okay? But if we're talking about atoms, they are all exactly the same. We wouldn't have to take an average of 10. We know exactly what they have, what they weigh. So we need to know, to figure out how many M&Ms are in the bag, we need to know the average mass of one of them and the total mass of the M&Ms in the bag, and then all we're going to do is divide. Well, this isn't a special number. This is called Avogadro's number. And it's a pretty special number because we know it's how many things there are in what we're going to call 1 mole. Okay? That's what we're going to call. That is a unit of measurement of how many things you have. Okay, 1 mole is 6.02 times 10 to the 23rd, whatevers. So the mole is the official SI unit for the amount of a substance. A good comparison for the word mole is the word dozen. The word dozen means a number. If I have 1 dozen donuts, everybody knows I have 12 donuts. If I have 1 mole of donuts, I have this many donuts. More donuts than have ever been made in the history of the entire world. But that's how many donuts I have. Okay, because it's a word that is a counting number. So like it's a dozen, 12 of anything. It is 1 mole of anything is 6.02 times 10 to the 23rd of it. So in particular, if we're talking about say gold, that means I have 6.02 times 10 to the 23rd atoms of gold. If I have 1 mole of water, what that means is I have 6.02 times 10 to the 23rd molecules of water. Okay, so it's a counting number. It's a word that means a number. Okay, it's also important in chemistry because that's what we use to convert grams to particles. That's how we use the mass to count things, just like with the M&Ms. I know how much 1 M&M weighs. If I know how much a sample weighs, then I know how many M&Ms I have. This is the same idea. We can count atoms by using grams. Okay? We want to react atoms with atoms. That's how reactions happen, right? It's at the atomic level. They exchange electrons and they form bonds, and that's how you get these compounds. But you can't count them because they're too small. So instead, what we do is we count them using the mole. And if you weigh out the grams of a sample, and we know how many grams there are in one of them, then we can determine the number of atoms that we have present in that mass. So 1 mole of M&Ms, just to let you know, is 6.02 times 10 to the 23rd M&Ms, probably more M&Ms than have ever been made in the history of the world. And it would weigh, I don't even know what the word is for that, a lot. Okay? So, the way we figure out how much 1 mole of everything is, we're going to set a standard. We're going to say that carbon, 12 grams of carbon contains exactly this many atoms of carbon. That is kind of our standard. Everything else is based off of this number in comparison using the weighted average. Okay, I remember doing the weighted average when we were doing in chapter, I guess it was 3 and 4 maybe? Maybe it was chapter 3 and 4. That's the atomic mass of the element. So the atomic mass of the element is 1 mole of the atoms of any element and 6.02 times 10 to the 23rd atoms of any element. So if I had 1 mole of, let's do gold again, that means I have 6.02 e to the 23rd atoms of gold. And the atomic mass of gold, if you look on the periodic table, remember this is the number that is a decimal number, is 197 grams. Okay, I think that's right. I'm going from memory here. Bear with me on that. So molar mass counts for compounds. So we're talking about compounds. So if you're talking 1 mole of water, it is 6.02 times 10 to the 23rd. Particles is kind of like the generic term. Technically, water is a molecule. It's not ionic. And it applies to compounds. And so what we're going to do is the molar mass, which is a little different than the atomic mass, is equal to 1 mole of the compound and 6.02 times 10 to the 23rd particles of the compound. So to find the molar mass, what you want to do is take all the atomic masses of each element and add them up. That's all you're going to do. So molar mass is what we're going to work on today. So what I want you guys to do is I want you to look up aluminum on the periodic table, and we're going to write down its molar mass. Okay? That means 1 mole of either the element, if it's an element, or the compound, if it's a compound. And what I want you guys to do is we're going to round it to the 10th position. Okay? That means I want to see a number after the decimal. That's for sig figs, and we'll talk about that later. So if you look up aluminum, it says 26.9 something something something. Okay? Well, it rounds up to 27.0. So yeah, for the aluminum, it says 26.98. We're going to round that to 27.0. Units are grams. Chlorine gas. Now let's remember that that's one of our Brinkelhoffs. That would be Cl2. It's important to know that formula. If you look on the periodic table, it says Cl is 35.45. Well, we're going to multiply that times 2 because there are 2 atoms of the chlorine, which means that I get 70.90 grams, or 70.9. You might even call it 71. Okay? It's okay. Doesn't matter to me which one you do, as long as you have that number there for sig figs. Doesn't matter. Now let's look up this one. Okay? So magnesium on the periodic table says 24.31, so I'm going to call that 24.3. And then the fluorine says 19 or 18.99 something something something. We're going to call that 19 times 2. I'm going to add that up on my calculator, and it says 62.3 grams. Now this one's a little bit more complicated. Okay? Remember that parentheses, that 3 distributes to each one of them. So I'm going to look at the nitrogen's number, 14.01, call it 14, and I'm going to multiply it by 3 because there are 3 of them. I'm going to add it to the hydrogen. It says 1.008. We're going to call that 1 times 12, because 3 times 4 is 12, plus phosphorus. You look it up, it says 30.97. We're going to call that 31, and there's only 1 phosphorus. And then the oxygen, if you look it up, it says 15.99999. We're going to call that 16 and multiply it times 4. And if you have a graphing calculator, pretty sure you can just go ahead and just type this in. So 14 times 3 plus 1 times 12 plus 31 plus 16 times 4. And I get 149. Now it's a whole number, which means I'm going to have to stick in that 0 to give it that sig fig. Okay? Why don't you guys stop the movie, see if you can come up with these two. Okay, and then we'll talk about this one. Alright, so copper I read is 63.5. Carbon is 12, but I want to multiply that. Remember, this 2 distributes to everything, times 4. Hydrogen is 1. I'm going to multiply that times 6. Now I'm going to add that to the oxygen, 16 times 4. And when you do all that, my calculator says 181.5 grams. For this one, it's 12 for carbon, and then there's 12 atoms, added to 1 for hydrogen times 22 atoms, 16 for oxygen times 11 atoms. 342 is what my calculator says, but I want that extra sig fig, so I'm going to put in that 0. Okay, now for this one, this is where dropping and swapping is going to come back and bite you. You got to remember how to do that. Okay, aluminum is a 3 plus charge, sulfate is a negative 2. When you drop and swap, you get Al2, SO4, 3. Okay, so those skills that we've learned, you can't forget those. Aluminum is 27 times 2. Remember that 3 distributes. Sulfur is 32.1 times 3, because it says 32.06 or 07. I'm going to round that up to 32.1, plus 16 times 12. And when I do all that, I get 342.3 grams. Now, recognizing that not a lot of people are going to remember to do 32.1, okay? It's okay, as far as I'm concerned. Ms. Packard doesn't care. Just recognize that when you're doing problems with this later on, your answer is going to be off by mine by a little bit, because I'm going to go to the tens position every time. And if you want your answers to match my answers exactly, then you better use the same number of sig figs I use. If you don't, you're not going to freak out over that, then that's fine by me too. That's totally your call. Okay?